Inside every modern electric vehicle motor sits a handful of magnets so powerful they can lift 1,000 times their own weight. But these magnets have a massive problem. They rely on a single element called neodymium. Neodymium is the heart of the EV revolution, but the supply chain is fragile and concentrated in just a few regions. If we want to scale green energy, we have to find an alternative, and we have to find it fast. For decades, materials science was a game of trial and error, a slow, expensive process of mixing chemicals and hoping for a miracle. But researchers at the University of New Hampshire just changed the game entirely.
The UNH team didn't just test a few dozen materials in a lab. They deployed an AI model to scan a staggering 67,573 different chemical compounds simultaneously. It's like searching for a needle in a haystack, but with a magnet that covers the entire field. This wasn't just a random search. The AI was looking for a specific Goldilocks zone, materials that are magnetic, stable, and can survive the brutal heat inside a high-performance motor without losing their strength. Out of those 67,000 candidates, the AI identified just 25 winners, 25 new materials that could potentially replace neodymium and revolutionize how we build everything from wind turbines to Teslas.
But why is high temperature such a big deal? Most magnets lose their stickiness as they get hot. In an EV motor spinning at 15,000 RPM, temperatures can skyrocket, causing standard magnets to fail instantly. To stop this, manufacturers currently add heavy rare earth elements like dysprosium. It works, but it makes the magnets incredibly expensive and even harder to source. The UNH discovery aims to bypass this entirely. These 25 new materials are designed to be high temperature by default. They maintain their magnetic alignment even when the heat is on, without needing the rare earth additives that plague the current supply chain.
This sounds like a total victory, right? Well, here is the catch. There is a massive gap between an AI saying a material should work and actually holding that material in your hand. This is the lab-to-factory bottleneck. In the computer, atoms are just numbers. In the real world, atoms are stubborn. Sometimes the AI suggests a crystal structure that is physically impossible to grow in a lab using current manufacturing techniques. The UNH team has to figure out the recipe for these materials. It is not just what elements you use, but the exact temperature, pressure, and cooling rate required to make them real. And that is where the real work begins. We are looking at a fundamental shift in how we discover the building blocks of our world. But to understand the true impact, we need to dive into the math that made this possible. Because the AI didn't just guess, it simulated physics. Coming up, we are going to look at the black box of material science and why these 25 magnets are just the tip of a much larger iceberg. The way we make things is about to change forever. To find these materials, the researchers use something called high-throughput screening. Imagine a supercomputer running thousands of tiny physics experiments every second, testing how atoms interact at the quantum level. Instead of building a magnet and testing it, they use the AI to predict the magnetic moment and Curie temperature of theoretical compounds. This allows them to discard failures before they ever touch a test tube. This process compresses decades of research into weeks. The AI acts as a filter, narrowing down millions of possibilities into a short list of high-probability candidates that actually stand a chance in the real world.
The AI uses a technique called density functional theory, or DFT. It is a way of calculating the electronic structure of many body systems. Basically, it predicts how electrons will behave in a new crystal lattice. If the electrons don't align correctly, the material won't be magnetic. The AI checks this alignment across thousands of permutations, looking for the perfect symmetry that creates a permanent magnetic field. It is a massive computational challenge. Even with modern GPUs, calculating the quantum properties of 67,000 compounds requires incredible efficiency in the code. This is where the UNH team's clever algorithms come in.
But here is where things get tricky. AI simulations assume a perfect crystal. In the real world, materials have defects, impurities, and grain boundaries that can completely ruin their magnetic properties. Skeptics often point out that computational discoveries frequently fail during physical synthesis. Just because a computer says a material is stable doesn't mean it won't oxidize or fall apart the moment it hits the air. That's why the lab-to-factory bottleneck is the ultimate boss fight of material science. You can have the best AI in the world, but if you can't cook the recipe, you don't have a product.
To solve this, researchers are now using AI to predict the synthesis path itself. They are teaching the AI to not just find the material, but to tell them exactly how to bake it in the lab. This is a massive leap forward. It turns the AI from a simple search engine into a master chemist. It is the difference between having a picture of a cake and having the exact measurements for the flour and sugar. And the results are promising. By narrowing down the how, we can move from discovery to prototype in months instead of years. This speed is exactly what the EV industry is screaming for.
So, we have the candidates, we have the process, but why does this specific discovery at New Hampshire matter so much for the global economy? To understand that, we need to look at the rare earth monopoly. The geopolitical implications are wild. We are talking about a future where energy independence isn't just about oil, it's about the very atoms we use to build our motors.
Right now, one country controls nearly 90% of the rare earth magnet supply chain. That is a single point of failure for the entire global transition to electric vehicles. If that supply chain chokes, the green revolution stops. By discovering 25 new materials that don't rely on neodymium, the UNH team is essentially building an off-ramp for this monopoly. These magnets can be made using more common elements like iron, cobalt, or nickel. This isn't just about cost, it's about sovereignty. It allows any country with a decent manufacturing base to produce their own high-performance magnets without being beholden to international trade disputes. But scaling up is a different beast. Making a gram of a new material in a lab is one thing. Making 10,000 tons of it for a fleet of trucks is another. This is where the factory part of the bottleneck hits hard. We need new types of furnaces, new casting methods, and a whole new supply chain for the raw materials. It is a multi-billion-dollar engineering project that will take years to fully realize. The good news? The AI is already helping here too. It is being used to optimize the factory layouts and the energy efficiency of the smelting process. The digital revolution is moving into the heavy industry space. This UNH discovery is just the beginning. Now that we have proven the AI can find 25 materials in one go, researchers are applying this to every other part of the EV. Better batteries, lighter frames, more efficient semiconductors. We are entering an era of software-defined materials. We decide what properties we want: strength, conductivity, magnetism, and the AI tells us what to build. It's like having a search engine for the physical world. The 67,573 compounds scanned at UNH represent a tiny fraction of what is possible. There are trillions of combinations we haven't even looked at yet. The library of human knowledge is about to explode. Here is my take. We often talk about AI in terms of chatbots or art, but its most profound impact might be in the boring stuff: the magnets, the steel, the glass, the things that actually make up our physical reality. The UNAH team didn't just find new magnets, they proved that we can use intelligence to overcome resource scarcity. We are no longer limited by what we can find in the ground, but by what we can imagine in the code. That is a genuinely fascinating shift. It moves us from a world of taking to a world of making, and that might be the most important discovery of all. The next time you see an electric car silently glide past, remember the 67,573 simulations that made it possible. We are building the future, one atom at a time, and the AI is just getting started. The question isn't whether we can replace neodymium anymore. The question is, what else is hidden in those 67,000 compounds just waiting to be found? I can't wait to find out.